For this video, we are going to provide the proper definition of a limit. But before we proceed to this, the reason why we discussed cluster points previously is because the definition of the limit for real analysis includes the idea of a cluster point. Because we will be having here the limit of a certain function at that given cluster point. So I'm going to write it here, and we'll have examples and illustrations later on using this definition. So we'll have it here. Let's say A is a subset of R, and let C be a cluster point of A. Take note that C may not be an element of A. C may or may not, rather, so it would work in that manner. So say for example here, for a function f from A mapped to the set of real numbers, a real number L, this is the notation for a limit, a real number L is said to be a limit of f at C. Take note, limit of f at C if given any epsilon greater than 0, so we're still going to use epsilon here, there exists delta greater than 0 such that, okay, if x is an element of A and the absolute value of this notation or a distance is greater than 0 but less than that set delta, then f of x minus that L is less than epsilon. This is the formal definition of a limit as we are going to use here in real analysis. Again, we have here A subset of set of real numbers and C be the cluster point of A, may or may not be an element of A. So for a function f, we have L as the limit of f at C. Given any epsilon greater than 0, there exists delta such that if x is an element of A and we have this distance between 0 and delta, then we will have this form. In the future identification or discussion of limits, we are going to use this definition, and if we can, we really need to provide results for existence of delta such that it would fit this assumptions and this result. If we cannot do that, then we cannot structure the idea of the limit. We'll have more examples of this in the next videos. We're just presenting here a definition for us to be guided onwards. Thank you very much for watching.